Hello, everyone. Welcome to the 2023 Systems Engineering Forum. Good morning or good afternoon, and thank you for joining us. To start, we are recording this event, so please keep that in mind. I am Alexander Chang, and I am serving as one of the co-chairs for the System Engineering Forum, alongside Dr. Alex Trujillo, who is helping me today. We will be helping to facilitate the event, transition slides, and capture questions throughout the briefing. Before I introduce our presenters, I'd like to provide a couple housekeeping remarks. The System Engineering Forum, hosted by the Aerospace Corporation in collaboration with the Jet Propulsion Laboratory, focuses on applying innovative systems engineering principles, such as model-based systems engineering, to mission success.
Hey, Alex, your mic is cutting off a little bit. I don't know if you want to redo that.
Once again, this event is both unclassified and is being recorded and will eventually be posted on YouTube. And this will include questions and answers that we say either by chat or by voice. The presenters today do ask audience members to use a chat box to ask questions, and they will address them as they are able. If you are asking a more complex question, please also use the chat box, and you'll be given an opportunity to elaborate during the Q&A sessions towards the end of their presentations. Please keep your devices muted and cameras off. If you're experiencing issues while using Teams, please reach out to Dr. Trujillo throughout the chat or sending a message through our website. With that, we can begin today's main events. Today's theme is Digital Twins, where we bring presentations showcasing the perspectives that the Aerospace Corporation and JPL have taken to apply and implement them throughout the life cycle. Our presenters are JPL's Robert Karban and Myra Lattimore, guiding us towards a model-based product development process from early concepts to engineering implementation, and the Aerospace Corporation's Denver Smith, Dr. Robert Stevens, and Dexter Becklund on Lifecycle applications for digital twins. Our first set of presenters is Dr. Karban and Myra Lattimore. Dr. Karban is a principal system engineer, the technical group lead of the Software and System Solutions Engineering Group, and the lead for the Computer-Aided Engineering Systems environment at NASA JPL. His team provides a digital engineering ecosystem for systems engineering and analysis activities to the engineers at the laboratory. Robert is internationally recognized as an industry leader in MBSE and MBE, using his leadership role in the open MBE community and as a NASA representative at the OMG for SysML to align the different model-based aspects. Myra Lattimore is a software systems engineer at NASA's Jet Propulsion Laboratory at JPL as a member of the Software and Systems Solutions Engineering Group. She supports the delivery of an integrated model-based engineering environment for engineers at JPL. She has worked on flight projects, including the Mars 2020 Perseverance rover, Mars Sample Return, Europa Lander, and Psych. Her professional interests include MBSE implementation, engineering environments, and executable system modeling. With that, we shall begin with our first presentation of the digital twins. Myra, you can go ahead and share your screen.
Alrighty, thanks, Alex. Right, and hopefully everyone can see my slides okay, right?
Yep, we got you.
Yep.
Perfect. So thanks for the intro, Alex. And as you said, I will be presenting today along with my colleague, Robert Karban, on work we have done called Taming Monsters with Dragons towards a model-based product development process from early concepts to engineering implementation. So over the course of this talk, we'll start out by discussing some of the problems that we are trying to solve, and then we'll talk about our approach for solving them. We'll present some of the examples on how these ideas have been applied to existing projects. And lastly, we will discuss some of the technologies that we are most interested in as enablers for this type of work. So that's the outline for today. So to start us off, what is the problem that we're actually trying to solve? So at the heart of things, we really like to improve our systems engineering. And to us, the role of systems engineers is to guide the concurrent collaborative design of complex technical systems. Now, this description is very simple, but we all know that actually doing systems engineering is really anything but simple, especially in the digital age. These days, we really ask a lot of our systems engineers. We ask them to lead the design of large cyber physical systems like our rovers on Mars. We ask them to manage complexity throughout the project. And on some of these deep space missions, the complexity is very, very large. But also large are the teams that we are working with. So I believe this photo here is of the Perseverance rover team and just a fraction of it. So there's a lot of people and effort that go into making these missions a reality. So we have a lot of people working on the projects and working on them through various phases of the mission, over the course of many, many, many years. And all these people on the team need to work together to accomplish the mission. And frequently, this is done starting with requirements in spreadsheets. And somehow, some way, these requirements in spreadsheets ultimately need to translate into this. For example, this is the final descent of the Perseverance rover on the Martian surface. So we go from spreadsheets and requirements to this, or even something like this, where we are flying the Mars helicopter on the surface of Mars. So kind of a big transformation from those early requirements in spreadsheet to these really amazing technical feats. And it takes a lot to get us there. So the question that we spend a lot of time working with is, how do we go from kind of these simple representations and requirements to something really crazy and complex and amazing at the very end? So it takes a lot of people, a lot of requirements, a lot of spreadsheets, documents, processes, workflows, and tests. And it's pretty messy, honestly. We frequently end up with silos information that lead to miscommunication and duplicate work. And it really sneaks up on our projects because, so often it starts out so simple and so well scoped. But engineers, they work on their models, they iterate on their models, they enter data into their roll-up, they add it to various spreadsheets to track it over time. They may add it to a document, get lots of input from others throughout the course of various meetings. And so the data changes and it gets very complicated very quickly. And so we end up in a situation where we have very complex spacecrafts with more functions, more hardware, more software, and it becomes difficult to know how a single change impacts the system across the board. It becomes hard to understand relationships between these silos information, like how to do even maybe a simple thing like check a requirement against a test. And we end up with disconnected areas or implicit relationships that few people really know about or understand. And the qualification process does not work systematically. So it becomes difficult to certify our systems. And I think one of the key points that we experience, and I'm sure our other organizations do as well, that ultimately we end up with a bad ratio of real engineering to overhead. So rather than making meaningful technical progress, engineers spend a lot of time entering data or figuring out which version of the data is the correct one to use, and constantly searching for the pieces of information that they need. And really, I think all projects can benefit from minimizing overhead and kind of redirecting that effort towards more novel engineering. So the key challenge that we focus on a lot is how to connect all of these spreadsheets, these documents, these models, and data together. So that is our problem. So how can we solve it? What can we improve about our systems engineering and development process to address this problem? How can we use dragons to beat our monsters is the analogy that we'll use. So our monsters are really our information silos. And what is scary about them is that they have a lot of implicit connections. So for example, there might be many implicit relations between our flight software, our ground data system, and our spacecraft components, and they may not be well understood, but we can use models to formally capture these relationships. So basically take these implicit connections and make them explicit and well-defined. So we try to weave together a digital thread between the silos to provide traceability and thus better clarity about our system. So this concept of transforming implicit relationships into explicit relationships is really the cornerstone of the kinds of digital twins that we are trying to build. So on the left here is our system development process, which follows a spiral development approach that iteratively adds increasing system definition over time. And in parallel, we have the development of our digital twin. So our digital twin starts very simple with a few basic representations of our system. And this can be in the form of model or code and tests. And each piece of our digital twin corresponds to some aspect of our system. And eventually, the intention is that it evolves into the implementation of that system. So over time, we connect added capabilities to our digital twin to build up that twin capability in step with the development of the real system. One important thing to note is that at each increment of the digital twin, so as we're trying to add to it and build to it, basic validation is performed to ensure that kind of the models that we're adding to are valid. So this could be achieved by something like executing your models, so model simulation or model checking, for example. And we kind of try to validate each little piece as we add it on. So we call this the fractal development of digital twins, since each component of the digital twin can be considered self-similar in the sense that it's a validated representation of the system. So for those of you that are following the monsters and dragons analogy, the dragon actually comes from the reference to the mathematical dragon curve, which is a family of self-similar fractal curves. So you can look that up, but this graphic kind of shows what one looks like. But the monsters are the silos of information, and the dragons that slay them are the fractal development of digital twins. So very fun. So this is the approach that we've been trying to implement and to realize. And there are a few big advantages to this approach. I'd say that first, you build and analyze your system digitally before you commit to buying hardware. So you define your system purely with software first, so a software-defined system. Second, you can qualify aspects of your system through the digital twin. So this is particularly handy when access to hardware is limited. Fortunately, computational resources are a little bit easier to procure. And I'd say that this is something that I personally benefit from working on JPL flight projects. For example, I work on the Psyche mission right now, and we only have 3 physical test beds. But fortunately, we have access to a spacecraft simulation, and that enables us to work independently of the test beds. And as you can imagine, with lots of things to test and only 3 hardware test beds, being able to run things in simulation allows us to make a lot of progress and do a lot of development just in the software and simulation space using a digital twin rather than needing to use a physical test bed or even the actual spacecraft itself in Atwell. So I think that's one of the main realized gains from this approach. And lastly, it enables traceability across system development that breaks up our information silos and facilitates auditing our engineering process. So when set up properly with the right traceability and repeatable processes, it's a lot easier to go back and see what you did at any point in time, or go back and understand the state of your system at an earlier time. So we end up with a repeatable, executable representation of the system and its relationships at different levels of fidelity. So how might one set up such a development pipeline? So this is an architecture view of the approach. And I know that there's a lot going on here in this slide. So I will just point out a few of the key features to keep in mind. So the first notable thing is that an environment of systems and software engineering applications and services is needed. And this is shown by some of the dark blue boxes at the top. And it's not incredibly important which applications and services are used to create your models or store your data. What's important is that the data is accessible or referenceable from other data sources. It just needs to be connected. So we may have some service for requirements management, some services for model and code storage, some services for model checking and testing, and for publishing results. So kind of a best of breed use of a variety of applications and services that contribute to this systems engineering environment. The second key thing to note about this view is that the process needs to be traceable. And by that, I mean kind of one thing leads to the next, which leads to the next, and nothing really exists out on its own island. So our requirements lead to some design specification, which lead to some executable models for analysis, which may then generate code that is tested and results are published. And one thing that kind of facilitates the traceability and the process flow is the use of techniques for issue management and continuous integration. And so those are concepts that we use that aid in achieving a traceable and repeatable process every time. And lastly, the concept of a change package is very, very important. So going through the process of turning requirements into design, into a model that is verified and then has some artifacts that are produced is a process that happens repeatedly during the construction of a digital twin. So each time we increase fidelity, we might go through this development process for another round. And kind of each time that we add an iteration to our digital twin, It's really important that we capture the additions, the subtractions, the changes, the test results, and documentation in a package that is archived. So really this collection of change packages over time is what enables the qualification record, so that we can go back and see what testing may have been done on this particular time frame, or what changes were added in a particular release, and things of that nature. So definitely a busy diagram, but key things are systems engineering applications and services create the environment. Things need to be traceable where one process flows into the next, and the concept of the change package is very important. So before we go into some of the examples, I just wanted to quickly pause to see if there were any questions up to this point.
Yeah, Myra, I don't know if you can see the chat, but we have one question of clarification of what is MMS under Teamwork Cloud.
Sure. So MMS stands for Model Management System. It's actually a service that's an open source service provided by OpenMBE. It's basically just a model repository, and we use it in a variety of ways here at JPL to store and access our model data.
Thank you. And there's another question. So systems consist of hardware and software. Is it difficult to twin, or it is difficult to twin a hardware? Can you list types of hardware simulations you can create, like functional simulations, etc.?
Yeah, so a lot of the stuff we're talking about today is certainly a little bit more focused on software simulation, but we do leverage hardware simulations at JPL as well. So when I was referring to earlier about some of our spacecraft digital twins, those simulations do also include simulations of the hardware. So simulations of our compute elements, for example. So some capabilities using Green Hills, or recently we've been looking into some capabilities with CIMIX, are used to in fact model at the hardware level.
Cool. There are a few other questions. There are a few other questions rolling in, but I don't know if you want to continue and wait to the end, or there's 2 or 3 more if you want to hear them.
Let me take a look. Actually, I can pull up the chat here.
Yeah.
So question, have you evaluated eCube as a digital backbone as an alternative to Syndea? I personally know. I know frequently at JPL we are users of Syndea. eCube isn't one I've looked at, but I'm definitely curious to know more. And then question from Brad, is this digital ecosystem based off of a standard, or is this homegrown based on lessons learned over time? So I say in some ways a little bit of both, and we'll talk a little bit later about some of the ways in which we're leveraging standards and standard languages and the way we use some more standard modeling processes. But also, parts of this are like this architecture approach are based on kind of our experience doing systems engineering at JPL. And then last question, I see SysML called out, any use for UAF? I personally, I'm not as much of a user as URF. I do believe we have a user community for UAF though at JPL.
Yeah, let me add, this is Robert speaking, let me add maybe something to that. I think in SysML v1, UAF is a profile of SysML, right? So I think there's no, UAF can be used as much as SysML, but our focus here is specifically headed geared towards the future with SysML v2. And if you look closely, the SysML has a little v2 there. So that is because of its textual notation and graphical equivalent notation. I think this is our future focus.
Yes, thanks, Robert. All right. So far we've talked a lot about theory, which is easy to talk about. But let's take a look at some of the examples where we've tried to actually apply some of these concepts on real flight project work. So the first example comes from Europa Clipper. And this example is related to testing of the Remote Engineering Unit, or REU. And the REU is a piece of hardware that flies on many JPL missions. And in this example, the Clipper REU team had a repository of requirements, and they needed to execute a test campaign against those requirements. So first, the team used a test management service, in this case it was TestRail, to specify their test cases and configuration. And then they used a traceability service, in this case Zendaya, to create explicit relationships between those test cases and their original requirements in their requirements repository. So this construction of a digital thread, which connected requirements to test cases and configurations, enabled the team to generate traceability reports. So this is kind of an example of one seen here. And these reports kind of more explicitly revealed the connections between requirements and test cases. So this type of setup enabled the team to better understand questions like which tests are used to satisfy this requirement, and vice versa. So this is just a simple example of some of the ways in which we're trying to kind of shed light on or more explicitly define the relationships between our systems engineering components. The second example that we wanted to talk about is one that is currently being leveraged by the Mars sample return team. And this capability is to connect data repositories to web-based engineering documents. So in the case of Mars sample return, an integration between their requirements repository and their engineering documents enables them to directly reference requirements data within their documents. So this is an example of what that might look like, where they have a document with some text and a live reference to a requirement that has some of the requirements information available when you hover over the link. And so they can have inline references to requirements within text, or run queries from their document to produce tables that are embedded in their document with live data. And so these links in their documents are live links, and data updates are automatically propagated throughout the entire document. So this is one way that they're making sure that data does not become stale over time, that you don't need to manually go and update all the information in your documents, but rather you link it together, and you're able to keep your documents up to date as your requirements data changes. So this is just a quick video, kind of skim through it that shows it in action. This might be one of your documents that you may go in and edit. And as a systems engineer, you might want to insert a cross-reference to your requirement. So you insert a special character and search for the requirement that you are interested in. Once you find that requirement, you can select it and either reference it by its ID, by its name, or by its requirement text. We just fast forward a little bit. We can see what that looks like when published. So we have these live references to our requirements. And if those requirements change, we can automatically update our documents with the updated material. And we can also create tables. So create a query, in this case, querying by requirement ID to just find the set of requirements we're interested in displaying in our engineering documents, selecting them to form a table, and we can publish this table as well directly within our documents. So this is a capability that's currently being leveraged by MSR to create their design documents. So those are just some simple examples of the ways that we've tried to add better traceability and reveal implicit relationships for flight project work. And the next few examples show some a little bit larger pipelines that kind of aim to connect steps in the system development process. So this first example is mainly from the flight software domain. And in this example, state machine models of flight software behavior were constructed such that they could be simulated to verify high-level behavior. So think state machine and creating some state timelines that show the interactions between components. A traceability service, again, Zendaya in this case, was used to explicitly relate some of the project requirements to those executable model components. And a code generator was used to generate code directly from those state machine models and create references to those requirements within the source code files. So we have kind of the starting point is this executable model, which is able to generate code as well as the associated test code for the capability, and also produce source code references to the requirements that portion of code addresses. And the last capability kind of at the end of this pipeline is that we're actually able to generate documentation from the setup. So after generating our code from our models, also generate the documentation where those direct references to requirements that are in the source code can essentially be aggregated and create relationships to the requirement repository to the GitHub commit of the source code. So the relationships between the source code and the requirements could then be added to a report that's included in the code documentation. So overall, an executable model generated code with references to requirements that were explicitly created and generated in a report. So that's one example of a pipeline. And I believe, based on time, maybe we'll do one last example that's a little bit more focused on early phases of design. So possibly before the point that you have working flight software. This example demonstrates how we might use early phase modeling to aid in the design effort. So our model-based development process typically starts with a collaboration and capture phase, where we capture high-level system components in a system model using a language like SysML, for example. And we construct models that may include both structure and behavior. And if there are some more physics-based behaviors that we also want to capture, we may do that in a separate model using a language like Modelica, for example, that's better suited for physics-based behaviors. And we capture descriptions of our system in engineering documents where the document data is referenceable via an API. So an example of that is Confluence Wiki, where maybe the entries in this table are directly published from our engineering models. So that's kind of the kind of first phase of this high-level collaboration and capture, where we're kind of creating our initial models that describe our system. The next step is the design phase, where we articulate the design space. And this is the step where we capture constraints and iterate on loosening or tightening those constraints in order to balance architecture design and try to get an engineerable or closed design at the end. So a lot of our design space exploration may start with like a functional description that is then mapped to like a more physical description. I think in this particular example, we used a service called SimCenter Studio that allows you to kind of specify your structure and some constraints and then generate some viable architectures. that then perhaps you could map to like a physical definition in a Modelica model, for example. So this is kind of the architecture and design phase where we kind of explored the design space and try to understand how our constraints impact our design. Then we get to the analysis phase where we may run simulations in order to evaluate our design. So I think in this particular example, this is just a kind of a visual simulation where we see that the model we've created, we can try driving it over a bump and seeing kind of visually how our system performs for that scenario. Our analysis might be something like simulating state machines. I know we're big fans of state machines and creating those state machine charts that show the interaction between components. Or we might do some simulations related to constraint evaluation. In this particular example, we had a system that used a battery and that the battery would drain over time. And we wanted to verify the behavior that when it hits some lower threshold, the system stops and begins to charge. So these are some examples of the type of analysis that we do. Again, kind of very early in the mission life cycle, where we just created these kind of higher level system models that we then want to simulate and execute to better understand our design. Also, fun fact: this rover simulation is open source. If you're into Modelica stuff, you can take a look. But these are just some of the simulation outputs to some of the work that we've done. Obviously, the visual ones look pretty cool, so I like to show them here. But this, again, is that open source Modelica model of the Mars rover, also of the Mars helicopter, where kind of using some off-the-shelf library components, we were able to create just a simple and fairly low fidelity simulation of the Mars rover without too much effort. Pretty pictures. And one of the capabilities we kind of really like about sort of this process and this pipeline we've set up is the ability to interface with these simulations through Jupyter notebooks. So in this particular example, we have a Jupyter notebook where we can vary the parameters of the model. I think in this example, it is running like the model that we see in these simulations. We can vary the inputs to the parameters of the model, rerun the simulations, and visualize the results all within a single notebook. So I think in this particular case, we were swapping out kind of a different wheel and plotting things like the velocity as we drove over a bump, or the battery state of charge as we drove over a bump. So being able to do this from a Jupyter notebook interface is a capability that we're really looking to leverage, where we can have our code and any documentation narrative and our visualizations all within a single notebook environment. Right. Before I move on to the last topic about some enabling technologies, are there any questions?
A few more have popped in the chat if you wanted to take a look. So there's one about, does Syndeia also provide interoperability capabilities between specific tools, or is that developed on an as-needed basis? Myra, can you hear us? You may have dropped off.
It looks like she dropped off.
All examples that we just talked about.
Oh, sorry, Myra,
you cut out. Yeah,
you cut out for a bit. Might want to restate that. Seems like Myra's having microphone issues. Robert, I don't know if you wanted to take the question while Myra tries to recover.
Yes. Yeah, sure. I'll just texted her that we can't hear her. That was about the interoperability with Syndeia. Was that the question? I guess.
Yes.
Right?
Yes. Yeah.
Yeah. So Syndeia has a lot of out-of-the-box integrations with different tools for traceability and mapping. And it also has a very capable REST API that can be used to, as we saw in these previous examples, to create those connections and traceability as part of your workflow, which is kind of I think what we are shooting for. Right? So you can create them manually, but for example, if you generate code, if you transform a model, you can build in this traceability and generate those connections as part of that process. The interoperability is REST API based and out of the box mostly.
Gotcha. Myra, I see you're back. Can you hear us now?
Yes, I'm back.
Okay, there we go.
Teams let me know that they were sorry, but they dropped the call.
Oh no.
Yeah.
Well, welcome back.
Yes, glad to be back. What was the last thing I said, Robert?
I answered the Syndeia question.
Oh, good. Okay. Nice.
Yeah, there are a few other questions in the chat, Myra, if you wanted to take a look, or again, maybe we could wait till the end, however you want to do it.
I think we'll wait till the end and make sure we get through this last section and leave enough time for some questions. But we can still see my slides, right?
Yes. Yes.
Okay. Great. So last topic, enabling technology. So we'll kind of cover some of the concepts and technologies that we think are really driving us towards realizing model-based nirvana. So I think one of the kind of capabilities that we use in various ways at JPL is the open model-based engineering environment. So OpenMBE is at its core just a community for open source modeling, software models and other types of models. So as I alluded to earlier, like that Medelica model, the rover, is something that's available to the OpenMBE community. MMS is the model repository that's also part of the OpenMBE environment. But I think we use a lot of OpenMBE components in our work. But really, I think the key enablers is open source in general. The ability to leverage work that people have already done, and to be able to reuse capabilities that folks have developed and kind of not reinvent the wheel and have a good starting point is really a cornerstone of a lot of work we do. So we're big fans of utilizing open source capabilities when it's applicable and when it makes sense. So the next kind of capability that we think is really enabling, or really the vision, is one kind of multi-language environments. So I think through the course of this presentation, we've had some references to doing SysML modeling, to doing Medelica modeling, use Python for a lot of different things. So building these multi-language environments that allow you to kind of translate your data between languages, between models that might have been written in different languages is really important. We also think that having these model analysis and model simulation capabilities as a service is really important. We found at JPL that when we can provide environments as a service versus things that people have to download and set up, it smooths the user experience and allows us to have frequently better integrations, because sometimes if it's a service, it might have an API and it might be easier to get your data in and out. We are also think that kind of commoditizing these systems engineering processes or these pipelines kind of brings value to the organization. So rather than every flight project having to kind of figure out their own process for building their models and simulating their models and getting results, kind of providing an environment with some supported general workflows as a commodity, provides a good way for flight projects to adopt our systems engineering processes. And then lastly, standards are a really big part of our vision. So using standards like SysML v2 in the future and standard API and services are really important in helping to build a modeling environment that's interoperable. We can bring in new components and you don't have to do as much custom development. So I think those are some of the key capabilities. Another one is really Jupyter as analysis and visualization hub for models. So our Jupyter environment is really a cornerstone of the work that we do because it allows us to not only develop and simulate and visualize in one location, but really to kind of bring together model information from a variety of sources and provide it to the user in a clear and concise way, either through some sort of dashboard or some nice visualizations. So also the Jupyter environment includes a lot of open source components. And so we use it a lot in a lot of our processes. Another key enabler is SysML v2. So we've done a lot of work in the SysML v1 space, and we're really excited for the future capabilities of SysML v2. I think, for example, really excited about standard API to access the model. I'm excited about some of the vendor tooling that will hopefully be available for building our SysML v2 models. This language, we feel, in addition to other languages like Modelica and Python, will continue to play a prominent role in a lot of our modeling practices. Next key technology is functional mockup interface. So if you're not as familiar with this, FMI, or functional mockup interface, is a standard that allows us to create kind of tool agnostic models. So you can those tool agnostic models are called FMUs, or functional mockup units. So you can kind of think of it as sort of a black box for your model with just your interfaces exposed. And so we use this technology to maybe define models in one language, but bring them into in a simulation environment that might use another language. Because really what you need is a simulation environment that supports FMUs that conform to the FMI standard. And then you can kind of treat your models like Lego blocks and plug and play them because of this kind of standard interface. So FMI is another kind of enabling technology that we're looking to better leverage for some of our modeling efforts. And I think lastly, packaging capabilities and distributed capabilities like Conda are one of the key enablers for our vision. So being able to specify your dependencies and create packages of your models and distribute them as self-contained packages that then lend themselves well for reuse is another capability that we think will enable our vision. So last slide, we always joke about what the next generation systems engineer dream car looks like. Well, it has kind of Jupyter as the engine and open source as the framework, and things like Conda, FMI, and SysML v2 and Modelica as some of the wheels and features. So that's just a little bit about some of the technologies that we think are really going to kind of drive our push towards model-based product development. All right, with that, I think we can take some more questions.
Great, thank you so much, Myra. So there are a few questions in the chat, some having to do with or a lot of them having to do with the tools, right? So Michael asks, can you say where you got the tools needed to implement SysML v2?
Yeah, so good question. So we don't fully have a SysML v2 tool just yet. We do have a service called SimCenter Studio, which has a proprietary language, which is very similar to SysML v2 right now, and I've been told will hopefully evolve into SysML v2. So we're not quite there yet. I think if you're involved in the development of SysML v2, we're still kind of going through the process of specifying it. So it's a little early to have wide selection of SysML v2 tools just yet, but we are very excited to get them in the future.
Yeah, let me add to that. So the last version of SimCenter Studio actually implements v2, and we did some initial experiments with that. But since it's not released yet as a standard, so there's an official standard, but commercial vendors are implementing something. And as far as I know, that's one of the first ones. But I see that Sandy Friedenthal is also online, so maybe he has a comment on that.
Yeah, and feel free to unmute, Sandy, if you're on the line and wanna speak.
I don't, thank you. I don't really want to speak for the vendors, but the beta specification for SysML v2 should be approved by the OMG. I'm expecting that to happen this month. So probably before the end of the month, or certainly in the immediate near term. It was submitted back in February and presented in March. And so it's in the finalization phase, and there's several vendors that are implementing v2. So hopefully their commercial tools will be available, sometime we're expecting, over the next year to start seeing the commercial tools available. In the meantime, we have the reference implementation, or what we call the pilot implementation, in Jupyter and Eclipse, which is a rigorous implementation of the language, but it's not and it is open source, but it has very limited visualization capability. Back to you.
Great, thanks. So we're talking a question on software development, and are you using UML for that, or UML tools for that?
So I'm a little bit less plugged into like the flight software development domain, but I believe, yes, there is a community of users for UML for software development at JPL.
Great. And so I guess Karen is asking, what do you mean by Jupyter as the engine of the car?
Yeah, so we use the Jupyter environment in a lot of different ways, but we use it frequently as a driver for a lot of our analysis and simulation. So even though we might, define our models elsewhere using some other development tool, we have a couple of different examples where, those models are simulated on a server. So we drive the execution of those models through a Jupyter notebook. And so we press play from the Jupyter notebook and we get the results back in the Jupyter notebook, and we analyze them there. And then from the Jupyter notebook, we might, publish them to some repository elsewhere. So in many ways, Jupyter is an integration point for a lot of our processes. It's really at the center of it all. So that's what we mean when we say that that Jupyter is the engine of our systems engineering car.
Got it. All right, we have 1 or 2 more minutes, let's see, before we need to transition over. Can you go into more detail onto the data-driven analyses as a service? The as a service portion is where Brad is unclear.
Yeah, so I think that's kind of a little bit like what I had just mentioned, where sometimes we construct our models, outside of our Jupyter environment. So they might be like a physics-based model, for example, using Modelica and model on impact. And so kind of all that definition and knowledge about the system in that model kind of, lives elsewhere. But because it's available as a service, folks can consume that model information from a variety of other places. So selectively choosing applications that allow us to create and store our models somewhere that can then be accessed through like web services is a really important concept for us.
And do you work with Open Caesar community as well?
A little bit. Yeah, a little bit. I don't personally work with them that often, but I am somewhat familiar with their work. They've done, my understanding is, made some good progress on using models and applying model-based systems engineering to harness design, particularly on Europa Clipper.
And there's one last question on Doors Next Gen. You showed that the DNG ID is your requirement number. Is that the standard for getting a requirement number? And is that used across the tools?
So we do use that requirement ID kind of across a variety of references. So I would say yes, we do use that DNG ID kind of as a reference for an individual requirement.
But it can be really any requirement ID, specifically DNG. Whatever requirements platform you use, it's not bound to that.
Great, thank you. I think that's it in terms of the chat. Don't know that there's any other questions, but I'm sure you guys can continue to answer them in the chat if people have them while we move on to the next presentation. Alex, I think we can send it back to you, but thank you, Myra and Robert, so much.
Thank you.
Yep, thank you. I should be sharing my screen again.
You are.
Okay, well, we don't plan on starting until the top of the hour. So if you'd like to take a short break for about 3-ish minutes, we will take a little bit of a pause, and you can continue the conversations in the chat. But we will start with our next presentation with Denver Smith, Dr. Robert Stevens, and Dexter Becklund on digital twins lifecycle applications. So taking a few moments. Okay, we are at the top of the hour. Our next presentation is Digital Twins Lifecycle Applications with Denver Smith, Dr. Robert Stevens, and Dexter Becklund. Denver Smith is a senior engineering specialist in the Aerospace Digital Engineering Integration Office. In his role, Denver leads key elements of the aerospace DE transformation effort, specifically capability development in the area of digital twins. Denver works to establish functional digital twins across the entire product life cycle for aerospace internal projects. Through this work, a digital twin specification and framework are being developed that focuses on the practical application of digital twins. Prior to joining aerospace, Denver served as the Digital Engineering Strategy Program Manager for Los Alamos National Laboratory. While in this role, he led the digital engineering transition for the Weapons Engineering Directorate, moving towards enhanced model-based capabilities across the weapons lifecycle. Rob Stevens is the director of the Model-Based Systems Engineering Office at the Aerospace Corporation in El Segundo, California, where he has provided systems engineering analysis support for numerous satellite programs, managed the corporation's concept design center, and served as a project systems engineer for several CubeSats in the AeroCube program. He currently manages teams that specialize in system modeling, space system concept design, concurrent engineering, space warfighting, and spacecraft digital twins. Prior to joining the Aerospace Corporation, he served in the U.S. Navy for over 20 years, operating, developing, and testing aerospace systems. Dexter Becklund is a senior member of the technical staff in the Vehicle Engineering Department, part of the Engineering and Technology Group at the Aerospace Corporation. Dexter has been at Aerospace since January 2019 and has focused on an array of topics during his time here, including space vehicle AI&T, small satellite expertise, as well as space system modeling and simulation. Early in his time at Aerospace, Dexter performed a variety of analysis for communication systems, which then evolved over time to his current role leading the modeling and simulation effort known as Aspen, one focus area of the discussion today. With that, I'd like to turn it over to the presenters to share the screen. Denver, I believe you'll be taking over.
Yes, thanks, Alex. Are you guys able to see my screen?
We are able to see your screen. Thank you.
Okay, perfect. Okay, so we're going to be discussing the digital twin over its life cycle today, and we're going to be touching on a few different topics there. We're going to be looking at overall architecture of that, as well as what does that look like in the early conceptual phases for some satellite applications, and then an integration framework that we're developing around space vehicle digital twins. And so those are the three things we're going to focus on today. I'll start us off as we discuss the life cycle architecture. So one of the big things that we've been doing here at Aerospace is trying to really understand this concept of a digital twin as it exists over the entirety of an acquisition program. There's a lot of examples out there of a digital twin that focus on a singular functional capability at a specific point in time in the program, usually operationally focused more often than not. And we are trying to take a step back and say, well, what does this look like holistically? How does this digital twin evolve and change over the course of its life cycle and support the physical system at many stages in its life cycle? So we're doing this in a couple of ways. So one is the specific application of this approach. And so we are taking a CubeSat program that we have. It's the Rogue CubeSat program. And we're looking at different points in its life cycle and developing digital twins that represent what we would be doing at that point in the life cycle. And it's a way of it being a test bed for us to really evaluate how is the digital twin effective at a given point in time, and how does it best serve the program. In addition to that, we're trying to generalize that approach. We recognize that as you're doing this, you start to do very specific activities dependent on your program. You pick very specific tools, you develop very specific processes based off of the program. So what we're trying to do is understand in a generalized sense, what are these approaches that we're taking with digital twins so that we can leverage this framework broadly across a wider customer base. And so how can we use this approach for a lunar lander, for a launch vehicle, for a satellite, for a tank, or a different weapon system? There's a myriad of challenges and problems out there. How can we generalize the framework so that it can be a jumping off point for developing a digital twin for these acquisition programs? So those are the key focus areas that we're looking at right now. And the way we're trying to go about it is looking at it with respect to this 5-dimensional digital twin model. Most of the time when people start approaching digital twins, they start thinking of in 2 dimensions. You have your physical and your virtual aspects of it. As you start to dive into it a little bit more, you start to realize that the data layer is so rich and so detailed that it becomes its own dimension. And so then you start thinking about it in terms of a physical system, a virtual system, and this data layer. we're really taking it kind of the next steps beyond that. And that's where we start to layer in this concept of connections and services. And so connections is, how is all this working together? How are we interacting between the physical and the virtual? How does the data get where it needs to go? And then the services really looks at the functional output of the twin. What is the twin doing? What is it providing? What are you interacting with? And so we're taking this 5-dimensional digital twin approach, and we're looking at how does that approach evolve over the course of a program lifecycle. So as we start looking at it, one of the first things we're doing is moving away from this concept of the digital twin as a singular model. And some of there's a myriad of definitions out there. Some of them allow you to take that approach where the digital twin is just a model of your system. We're moving beyond that, and we're describing the digital twin as more of a virtual system. And it's a virtual system that evolves with your physical system. And as we go through and we do this, what we quickly realize is that the virtual system goes through a similar life cycle that your physical system goes through. You're going to identify use cases for it. You're going to develop requirements around it. You're going to design your system. You're going to test and validate your system. And then you need to sustain your system. So these concepts that are true of a systems engineering approach to our physical systems, we find they're very true as well to our virtual system. And so now what we have is two systems that are growing in conjunction with each other, that are deeply tied together. They're informing each other throughout the developmental life cycle and moving in tandem towards this end goal. And so we really start to treat it as a virtual system, and you'll see more of that here in the next few slides. But one of the things that we've kind of teased out with this is this fidelity model and understanding fidelity of the physical versus the virtual over time. And what we see is early on in the conceptual phase of our programs and the early design phases, the virtual system really leads in fidelity, and the digital twin leads that fidelity. When you're going and asking, where's our program at? Where's our design at? What's the state of our system right now? You're going to your models. But eventually you hit an inflection point, and that's when you start producing a lot of components. And now all of a sudden you have, when you're going to the program and you're asking the state, you're looking at test results, you're looking at physical components you've built up in your assemblies and sub-assemblies. And so now the physical system is leading in the fidelity level, and the virtual system's trying to catch up and adjust to all those changes that are happening in the physical system. And then ultimately you hit kind of the operational life cycle of an acquisition program. And then it kind of is a play back and forth between the two. You get new physical data, and so that's your truth. And then you update your models and you make predictions about the next several days worth of activities, and that's your truth. And so it becomes this back and forth play between both of those. Now, one of the key differences that we have identified and have seen is that difference between operational functionality. So with your physical system, there's usually kind of a singular transition where an operational capability comes online. And that's towards the end of the development and right before you go into your operational phases. Where your digital twin is a little bit different is more often than not, you've identified multiple operational capability or functional capabilities you want the twin to perform. And by identifying those functional capabilities, those are going to come online at different points in the program. And so the digital twin does have a slightly different life cycle there, and that you ultimately have multiple points in time in which your digital twin becomes functional, and you have to be ready to plan for that and incorporate that in your approach. So as we take this approach, we have kind of this cartoon version of our general architecture up here, and you could see the 5 dimensions as well as the users shown. So your virtual entity, this really starts to focus on your models. It's your system descriptive models, your geometric models, analytical models, process models. It's a wide array of simulations and abstractions of your system. Your physical entity consists of your system, your components, your subassemblies, but it also consists of the environments that your system lives within. So what are the environmental conditions it went through during manufacturing? What is it going through during transportation? It's capturing all that environmental data as well as data directly from the system. We have this data dimension. It has physical entity data, it has virtual entity data, it has institutional data, it has legacy data from prior programs. It may have national standards and things like that tied into it. And so it's more than just gathering a little bit of sensor data or the outputs of a model. It's much richer and more in depth than that. Then the services dimension at the bottom. This is what most people think of when they're trying to visualize what a digital twin is. This is what the user is really interacting with. It's the dashboards, it's the visualizations, it's your ML analytics, AI analytics that you're applying to it. And maybe it's also even the point where you are interfacing and providing system commands to your virtual systems as well as your physical systems there. And it could be that touch point with how you're driving everything. But at the heart of all this is ultimately this connections dimension. And this is where your data brokers sit, your workflow managers, your APIs. This is how we make everything work. It's how you get the virtual and the physical to talk to each other. It's how you pull in that data. It's how you provide it out as a service to the user. This is the heart of what we see as being the digital twin. So we have this generalized architecture and some processes around it. But as you go to a specific program, you can really start to tease out, okay, well, what does this look like for my program? And so right here on the bottom right, you see a low fidelity MBSE model of the digital twin at the concept phase. There's not much to it. It's actually pretty easy to manage. The process flows are pretty simple. It's fairly intuitive, and the framework approach is probably a little bit overkill for something like this. But as you mature in your program and you go to your design phase, things quickly start to explode on you. So this top box here for these ATOP models, there's probably 20 different models that exist within that, 20 models that we have to integrate with each other, 20 models that we have to integrate with the rest of the system. And that's just one suite of models that we're applying here. And so very quickly, you see this rapid expansion in your models and your data sets and things like that. And this is where that connection layer and this framework approach becomes critical. The connection layers helps you to manage all of those relationships, and this framework approach helps you to manage the complexity of all of the data that you're pushing and sharing and pushing back and forth. Now, if we start to look at this as you transition out of this design phase and you start to move more towards the manufacturing phase, you're going to see explosive growth in the physical entity. You're seeing test data coming out of it. You're seeing manufacturing data coming out of it. You're seeing a tremendous amount more complexity being developed as well. And so this is why we're approaching it with this framework perspective as a way to manage the complexity of this growing digital twin, this virtual system, as we mature through the program. Now, some of the things that we see here are we can take our existing processes and we can start to bend them, right? So we have our life cycle going from left to right and some functional capabilities that exist going up and down. And we can quickly see that when we start talking about the virtual entity, all those models currently exist in our program. We're developing descriptive models, CAD models, geometric models, our physics simulations, maintenance models. We're developing all of those models currently. They exist for us. At the same time, we're building our physical system. We have our components, our subassemblies, our assemblies. We have data on all of the different environments that they're walking through. We're gathering operational data all the time. And so then you also see the blue layer there, right? That's the data that we're gathering. So we're gathering data related to the virtual entity. We're gathering data related to the physical entity. We're pulling it all in together. So this is how we're doing our programs as they exist right now. As we're approaching it with the digital twin, what we start to do is we identify functional capabilities that we want. So maybe I want a state of health dashboard, or I want to do integrated V&V activities or HillSil, or maybe I want to go through and explore certain operational approaches or operational parameters later on in its life cycle. So I identify the capability, and when I identify the capability, then I have to identify, okay, what data, what models, what physical system information do I need to pull together to provide that for myself? So we go through and we start to identify those needed entities, and then we build out our connections. And so we tie in, and so let's say we're doing the state of health dashboard. I need to pull in from my record of assemblies, my inspection data, my operational data, my maintenance models. I'm pulling all of that stuff together, connecting it together, and getting an emergence, getting this new dashboard that tells me a new set of information I haven't had before. I'm pulling in operational data and physics simulation and tying that back into information from my assemblies and giving myself new predictive capabilities for my operational exploration. And so we're seeing this approach where you identify the use cases, you identify what exists within your current programs or your current processes, and you're connecting it together to have this emergence of a new capability. Now, one thing I will say with this is that while within the virtual, physical, and data entity, 90% of what we need already exist, oftentimes it doesn't exist in the format we need. And so I may be looking and saying, I have power models that provide a physics simulation for me. But when I'm trying to make this connection and pull it into this operational exploration, I may find out that the way I develop my power models are not conducive to that connection. They can't speak to the process. And so there is a decent amount of non-recurring engineering investment that is needed to take some of these existing capabilities, rethink the way we do them, and to make them and provide them in a format that is more conducive to integration. And so with this approach, really what we're trying to do is expand our view of the digital twin. And so it's really going from not just viewing it as, oh, a digital twin is a model, and even not even viewing it as, well, a digital twin is just a bunch of integrated models. Really, we're saying a digital twin is this system approach towards the virtual system. And so it's looking at it saying, how do aspects of models and the physical system and data and connections and ultimately services all work together in an evolving manner over the life cycle to provide the functional outputs that you're needing. And as we transition on, you'll start to see where aspects of the research that we're doing from both Dr. Stevens and from Dexter, that they're pulling together to and where they start to fit into this approach. So I'll go ahead and pause here, answer a couple of little questions before we transition over to Dr. Stevens.
So we don't see anything in the chat right now. If anyone does have a question, please feel free to drop it in there or come off the mute if you want.
Okay, if not, we can answer any at the end as well. If not, I'll go ahead and have Rob step in and continue this conversation.
Okay, thanks, Denver. So I'm going to talk a little bit about early life cycle applications of digital twins. And you can see pictured behind me is our aerospace's concept design center. And this is where we do collaborative engineering. We do concurrent design of spacecraft and ground systems. JPL, for those of you who are there, you're familiar with TMX and Innovation Foundry. Concept Design Center, CDC, is our version of that here at Aerospace. So we do a lot of concept designs. And so when thinking about applications of digital twins in the concept phase, it's a little different than when you think of it in the operational phase. And so one of the things that we have to consider is that for operational spacecraft, which a lot of the examples we see out there in literature, here, I'm going to turn off my camera because you've already seen the CDC and you've already seen me. So there we go. Is that you have a physical twin when you're talking about operational spacecraft to twin with. So your digital twin twins with your physical twin, and it seems pretty intuitive. In fact, in that picture on the right, you can see there's a digital twin, and then on the very far right, you can see the physical twin. And one of the features of a digital twin is that there's this feedback loop between data. So the digital twin will provide tuning data to the physical twin. If you're operating a satellite, for instance, it may supply some information to the satellite that helps improve its performance on orbit. And likewise, the physical twin will provide telemetry data about itself, and it'll actually give a more refined information to the digital twin, so you can improve the digital twin itself through the data. You can update the data, things like properties of the satellite, moments of inertia, things like that, that you can update the digital twin to make better predictions. And so you can see how that that works pretty well. If you advance one, Denver. But during concept development, there is no physical system yet. What does it mean to even have a digital twin when there's no physical twin to twin with? Well, first of all, you have to start somewhere. And so what we have initially is what appears to be a simulator, but and that's part of it. But you can have this feedback loop with your digital twin still. So as you're forming your digital twin, I'll show you an example of here that we're using at Aerospace in the Concept Design Center, is that your concept has definition data. You define it through requirements. You can also define it with some, if you're doing trade studies, you might have certain parameters that you're capturing in the form of data. So you have design and definition data that you can supply to the digital twin. And the digital twin in its early form can still be used to verify. You can provide verification data. For instance, those requirements I just mentioned, you can help verify some of those requirements through analysis. And in that way, you can help verify your concept early on. So there's this push and pull of data between your concept and your virtual system. Can you advance one, please? So one of the things that we wanted to develop in this concept development phase, especially in our concept design center, is to have this multi-purpose or general purpose, I should say, rapid and reusable digital twin model that you can just put your data set in there and then create instances of satellites. We do a lot of trade studies. And so one of the things we need to do is have this quick way to try out different concepts that we come up with. And so this general purpose reusable model we're calling SimSat digital twin model allows us to just ingest data sets so we can do quick evaluations and trades between anything from large satellites to spinners to small satellites or even CubeSats, all with our general purpose digital twin model. Next chart, please. So some of the characteristics, we set out requirements for our digital twin. I won't go into all of them, but one of them was to have this one-click access from the design data to the sim environment. As Myra briefed before, a lot of times we use spreadsheets to do these early concept designs. It's easy, everyone knows how to use a spreadsheet, and so we can develop our kind of rough objects, rough design trades, size, mass, power type relationships. And we wanted to have one-click access to a sim environment that allows you to ingest that data directly without having to manually enter in data. You can just go right into your sim environment and then try out your system. As shown on the right there, you can see that's an example of RogueSat, which I think Denver mentioned previously. I mean, the picture shown there is an actual completed. We actually have a physical satellite that does that. But imagine during a concept development phase, sometimes we're just dealing with just basic shapes. It's a cube, it's a box, it's got flat panels, it's a sphere, that kind of thing. Yep. Was there a question? Okay. I'll keep going. So what we wanted to do is have an integrated set of models versus a federated set of models. Not that that's true, an advantage in every single case, but in our case, for concept development, we have a certain set of models that we developed for uniquely for this process of concept development. And the key feature being is that we can ingest data directly from the sources instead of having to manually enter data in. We figured that users in the Concept Design Center would not use a sim if they had to do a lot of work to get there. Why not just stick with the spreadsheets and do your trade studies there with some rough analyses, which is usually oftentimes good enough, but sometimes you want to take it to the next step and actually simulate some of the concepts that you come up with. So we wanted to have this one-click access, and so one of the ways we decided to do that was using an integrated set of models instead of federating a set of existing models that usually require higher fidelity information as inputs, more so than we have at the concept level phase. So one of the things that we wanted to look at is, as we're developing this digital twin, is look at future life cycle phases. I've been focused mainly on concept development, but as Denver pointed out and Myra earlier, we do have to recognize that the digital twin matures with the system. And so during concept development, as I've talked about, rapid trade space analysis is an important feature of our digital twin model. You get into preliminary design phase, you might need higher fidelity simulation data that will inform component selection, and you can verify those system level requirements. Then as you get further along, you want your digital twin to mature even more to verify component level requirements and specifications. As you get into INT phases, you may need your digital twin to support test planning by informing those test cases. Operations, you can use it to inform satellite operators to improve performance and troubleshoot any anomalies. And then even disposal, you can use your digital twin, as I mentioned, that feedback loop that you have via telemetry. You can get information as an example on your ballistic coefficient as an example. You can help use that for deorbiting estimation. Next chart, please. So as I mentioned, one of the key attributes of the digital twins is your data authoritative sources of truth, or ASOTs, and those data pathways. So in the picture on the right, you can see 4 types of data that we are dealing with in our concept development. One is spacecraft design data, and shown there on the picture on the right, you can see that it looks like a spreadsheet that's pushing data into there, and that's because that's how we typically capture in our concept design center or in concept development, how we capture those design data is just through spreadsheets. We'll push that data into the design database, and then it's captured there for use from all the other tools that need to access that data. The next level there, the next hockey puck under the top there, system definition data. These are things like requirements or any other type of system definition elements like verification activities or state machine data. And those are typically captured in SysML diagrams. It doesn't have to be SysML, but it could be other forms. But shown there, you can see the tool, whatever your tool of choice is, will push that data into that data repository for others to use as well. And then configuration data, I think of CAD. So those are your CAD data. I think of that more of a library more so than a database, but you can see how that data is just as important to capture different elements of your system that the other 2 sources don't. And then finally, simulation data. When you're running the sims, you may want to rerun it later. You might, a year from now, you might want to run a similar battery of tests on your system as it's further developed, or maybe you're developing a new system and you want to capture that simulation data instance every time you do that, so that others can access it as well. And I do want to emphasize that once the data is in there, then anyone can access it if you can make this accessible to others who have tools and other needs that need to access that authoritative data. Next chart, please. This just shows the data framework that we use within our digital twin model. This is not prescriptive. It's not saying this is the only way to do it. It's just showing a way to connect these different tools together. It shows an N2 format, which basically is a description of the different data needs, the pushes and the pulls. It's not supposed to indicate that any of the tools along the diagonal or any of those elements along the red there on the diagonal with the astropropagator, attitude propagator, and so forth. Those are the different elements of the simulator. It's just supposed to show the gazintas and gazatas, what things are produced by these modules and what things are needed by those modules. Think of it as kind of an interface control, so you can understand the different elements of data. You can define the data elements in any way you need to understand how things are shared within the tool itself. And these are the data types that are captured in the system definition data that I presented before. Next chart, please. So I'll just step through real quick the different types of data. As I mentioned, the spacecraft design data, often provided by spreadsheets. And you can see an example there of how you can capture size, mass, and power. When we're doing studies in the Concept Design Center, oftentimes we'll go through half a dozen or a dozen different configurations for a specific need that we have. And we want to capture that data formally. You might capture as config 1, config 2, etc. And that's captured as spacecraft design data. So I can store that in that depicted in that top hockey puck there. Next chart, please. Another type of data is a system definition data. And as I mentioned before, this is often captured in SysML type tools. You can see an example here. If I want to capture the logical behavior of some element of my system, for instance, it might be fault logic or attitude control. And I might one way to capture that more rigorously is in a SysML model shown there in a state machine. You can see the different states and state transitions. How do I capture that data for use in my SimSat environment? I can break those state machines down into their key attributes, such as the states, and capture the different activities that are going on while the system is in that state, and then I can define those state transitions. And so if I can break it down in that way, I can capture the system definition data. So anytime I want to run a simulation, whether it's one satellite or a number of satellites using that same type of logical control, I can do that and just pull it straight from that data source. So again, I'm using an authoritative source of data to capture this, so I can pull this out in the future, or I can link it to other elements of my system. If I'm trying to verify system activities, say further downstream in the life cycle, I can pull the data straight from the source here. In this way, it provides more or less a digital thread that connects my data together with other tools and models. Next chart, please. Physical configuration data, as I mentioned before, I don't think of this as a database, but more of a library. You see the example there shows for road, but we have any number of satellites that are captured in CAD form if I ever need to use a different satellite model to start with. For instance, if I am doing a new system design and I want to start with something that's already been built and maybe run with that as a starting point, initial condition, so to speak, I can use this library of CAD models that have been developed through the years. Next chart. And then simulation settings. Again, this is that will capture the settings that I do for any given run of the simulation. So if I want to use that for verification data downstream, say verifying requirements through analysis, I can pull up the sim data and then rerun any sim that I want with that captured data. Next chart. So what we want to do is build in hooks to allow us to link into the data in future life cycle phases. So once we do have an actual physical system, and not all of our concepts that we develop actually become to reality into a physical system, but some of them do. And so we want to build in hooks that allow us to update our model and our data based on real telemetry. So I mentioned that example of the ballistic coefficient. So if I put in a hook in my digital twin model to accept in a ballistic coefficient once that data becomes available through TLE or any other source, then I can have that hooked into my model so it'll automatically update whenever I get that new information, and it'll update my digital twin model. So those are some important things to think about when you're building a digital twin. For concept development, you have to think about future life cycle phases as you do that. Next chart. So I'd like to summarize before I turn it back over to Denver. Is a digital twin that we want to build for spacecraft concepts in a virtual space and environment will verify design requirements, and it enables a holistic analysis of both the logical control and the physics-based behaviors. So you're linking together different models and tools, all connected by the same data sources. The data necessary to run the simulation are generated by the different tools. So as I showed you in that picture showing the different hockey pucks stacked on top of each other, each of them had a different generating source. That was the authoritative model used to push the data in there. But once the data is captured in there, then any of the other tools throughout your organization, whoever has access to that data can pull it out. The digital thread that weaves through all those ASOTs and tools enable data consistency. So as been pointed out, I don't need to foot stomp this anymore. I think we've done a good job of that so far. Is that data consistency is very important to maintain between system requirements, design, and configuration across the life cycle. And then finally, digital twin integration starts early in the concept development stages, and you do this with established data pathways and well-defined schemas, as I showed you in that N2 chart. So where this fits in with Denver's picture, he had those 5 different elements, and so this fits best probably within the services element of what Denver was talking about. And if you recall that picture he showed. And so with that, Denver, I'm going to turn it back over to you.
Thanks, Rob. We did have a question in the chat. It says this is a DSM, design structure matrix, which shows data dependencies, right?
I was just referring back to that thing you were showing before that you said was kind of like an N squared. It's really just a DSM kind of data in, data out. It's pretty handy, right?
Yeah, it's a convenient way to often show interfaces between modules. The only distinction I'd make is that it's not really showing a direct interface between, it's not like I'm literally saying that module 1 is connected to module 2. Oftentimes but I do need to know and have data governance. I need to know who, meaning, which module or which tool or which model that I'm using provides what piece of data, so I don't have two modules providing the same piece of data that might be conflicting each other. It's just a way to sort all that out. So I think the short answer to your question is yes.
Okay, thanks, Rob. And then there's another question from Alejandro regarding seeing a digital twin as a virtual system and applying the systems engineering process to it. What does the verification and validation phase look like? I.e., did we build the twin correctly versus did we build the correct twin? How does the physical entity play into that? And so it's all good to address this one. And it's a great question, Alejandro. It's because it's challenging enough to apply V&V type activities to a singular model. We develop a model that's going to test our system or describe our system. We need to validate that model. Now what we're taking is we're integrating a lot of models and integrating a lot of data sets together. So those questions do come up. Well, how do we validate this? And there's going to be some similar approaches, but you've hit the nail on the head that you have to do two things there. You have to ask, okay, are these things functioning correctly, right? So are we getting the right set of data from this one and feeding it into this? And is all the physics that's working on in the background, is it operating correctly? But you also have to find a way until you ask yourself, is it answering the question we want it to answer? Or have we taken into consideration all the different potential ways, potential influencers on that question, or if we limited ourselves to only a particular subset? So you have to work through that and really take a strategic approach and a tactical approach towards, okay, do we have the right data flowing in? Are the models functioning correctly together? You then have to test, okay, is it answering the question we want it to answer? And then you touched on the last one there. It's how does a physical entity to play into that? And it's really, in many ways, you're using your physical entity to validate out your virtual systems. And so as you're doing this, you're taking the results back from your physical data, you're going back through, you're comparing it to your models and saying, hey, are we seeing the same thing here? If we are, great. If we aren't, why not? And using that to update your models and tweak your models and adjust your models to make sure it is accurately capturing what is going on in the physical system. Okay, so the next topic we'll have Dexter talking on Aspen, and I'll hand it over to you, Dexter.
All right, thanks, Denver. If you want to jump into the next slide. All right, so Aspen is, I have integrated simulation approach, but maybe it's better to say a federated simulation approach or an integrated set of federates to do space vehicle modeling and simulation. So this presentation is going to be mostly focused on the mod and sim aspect of digital twins. There's obviously many other aspects like connections back to requirements, post-processing all of that data, all of these kind of other systems engineering disciplines. And so, but right now with this Aspen project in particular, we're really focused on that kind of federated modeling and simulation approach. So our goal with this project is essentially to create an environment where we can virtually fly out a simulated satellite. This could include various ConOps, design reference missions, but really what we want to try and do is create a generalized environment and framework where we can do all sorts of various modeling and simulation for any of our customers. And so that could include, a large Class A mission in geosynchronous orbit, or it could be a more complex, potentially multiple satellite mission in low Earth orbit, among other customers that we have. And so we're really trying to focus on not so much how do we simulate one particular vehicle, but how do we create an environment to connect various simulation components in a generalized way. And so part of this and part of our federated approach is how do we create interfaces between those federates and models that can be easily swapped out and interchanged. And that goes all the way from the actual models themselves, say like a simulated model of a component on a vehicle, to actually swapping out that model with a piece of hardware. So that could include, you know, anything from actually setting up a sensor in a kind of stimulated environment versus, you know, or even like a flight computer where you have hardware and software in the loop for that test. Part of our end goal for this, when we have this kind of generalized framework, is to really reduce the amount of NRE that's required for every new simulation we want to run. So obviously, if we go and a customer wants to simulate some, you know, in-space assembly and manufacturing scenario, we're going to have to develop new capability to support, say, like a multi-body physics problem. So in those cases, you have to add in capabilities, but hopefully over time, some of those, you know, new developments will end up decreasing. So if we go to the next slide. So what we're basically trying to do here with this is, as I said, kind of give our customers a way to virtually fly out their missions and enable different outcomes from those simulations. You know, we want to be able to verify and validate various designs of missions to make sure that, you know, part of our business in this industry is making sure that, you know, various acquisition programs are kind of being built properly throughout that acquisition life cycle. We want to explore various DRMs, and we basically just want to support a large variety of customer questions. And as I said, that could be, you know, kind of a traditional space problem, or it could be some of these newer problems where, you know, we start talking about things like rendezvous and proximity operations, in-space assembly and manufacturing, and then all variety of edge processing, AI, autonomy. And so as a part of developing this capability, not only do we want to support things like digital twins, but we want to be able to have this flexible framework where we can model and simulate all types of different components and situations with these missions. So if we go to the next slide. So just kind of recapping a lot of what was said, I'm kind of jumping through these slides to get more into the implementation of what we're doing. So as I said, you know, part of this is figuring out how we go between a simulated environment and a hardware environment. So we want to be able to support all sorts of hill, sill, and mill or model in the loop testing. I've mentioned rendezvous and proximity operations. So we don't want to just limit ourselves to, you know, running a single vehicle. We want to support multiple vehicles, whether that be, you know, a small cluster or if that's an entire constellation. So kind of making sure that we're not siloed into this one sort of scenario. Another aspect and something that's becoming a bigger objective for aerospace is doing wargaming. And so in that sense, you know, we want to be able to connect up both from a simulation perspective, but also just from a software perspective with other simulation capabilities that are doing more of the air, sea, and land-based scenario generation and simulation. And so there's a lot of work that we've been doing with our framework to connect into some of those other capabilities. And then, as I mentioned, we are also looking at some of the autonomy work. How do we V and V autonomous systems? And how do we support various digital twins efforts? So if we go to the next slide. So this is just kind of touching on some of the life cycle discussions that have been coming up. We're also looking at that from the perspective of, when we are looking at a federated modeling and simulation approach, how do we go from sort of the concept level trade space exploration and then jump off from that and slowly develop additional fidelity as a program moves through its life cycle? And so part of that is, swapping out those federates. Perhaps later in the life cycle, we need higher fidelity federates that are more representative of the actual vehicle that's being built. And so that goes back to the whole discussion of making sure that we're focused on the interfaces of how those models come together versus the models themselves. So if we go to the next slide. All right, so how are we actually doing this? Basically, as I mentioned, Aspen is a federated modeling and simulation approach. So it's based off of a pre-existing capability within aerospace called Amigos. It's an acronym. I don't even know what it stands for anymore, but it's Amigos. It's based around a kind of publish and subscribe framework where the central broker is an ActiveMQ messaging broker. There are a set of management federates that help with things like simulation management, model initialization, time management, and then also data logging. And then we also have our client federates, which are essentially just all of the models that are connected up to that central broker. So those client federates are going to be, in this sense, with a space vehicle simulation type problem, could be all of those individual components of the vehicle, as well as any of the external simulations, such as the sort of truth models of the orbit or the attitude of the vehicle. And the way that all of those models connect up to each other is through a common object model. We call it our Amigos common object model. And basically that little blue bar on the left side of those client federates are that kind of ACOM or federate wrapper, where within the Amigos common object model, we have generalized definitions for all of the data that could be flowing through this entire simulation. And so each of those individual models can kind of speak their own language, but then when it gets passed into our broker, it gets translated into our generalized definition of data. So if I had let's say a model of a reaction wheel, and I wanted to swap that out for a higher fidelity model, all that is going to change within the overall federation is that I'm swapping out those sort of data exchanges between that one model, and none of the other federates are aware that something changed. So basically, each of these federates is completely unaware of each other's existence. They just publish and subscribe to specific data definitions, as well as topics where we can basically map specifically how data is being passed around. So it's a very nice way of sort of doing these sorts of large scale complex simulations and abstracting away a lot of that complexity. And a lot of this has been developed in the past with things like the high level architecture, or HLA, and then distributed interactive simulation, or DIS, and there's another one called TINA. So DIS, HLA, and TINA are three sort of industry standard ways of doing federated modeling and simulation, or distributed modeling and simulation. So if we go to the next slide. And this is kind of just a breakout from that previous slide of all the different pieces that we're currently working on with the Aspen project. I use Amigos and Aspen interchangeably. Amigos is sort of this overall framework of doing federated modeling and simulation, and then Aspen is this specific implementation of it with all of the specific models that are involved here. And so essentially what we're currently doing is just developing out all of these models, essentially building a spacecraft, but in software. And so working through all of these different aspects and trying to generate a bunch of very generalized models that we can use for a lot of different use cases. In addition to, besides just that kind of simulation approach, we're also working on the hardware end of actually building out the connectivity to various pieces of hardware. So if you go to the next slide. And then on the topic of building out capability for multiple vehicles, there's a way with federated modeling and simulation and distributed modeling and simulation to actually distribute out sub-federations. So if we imagine that one federation is kind of an entire vehicle, then we can sub-federate out multiple vehicles. And this is a great way of also multi-threading the problem. If we're just talking about, you know, high performance computing type applications, we can essentially thread each individual federate and run the entire federation in a very multi-threaded fashion. But basically, this is just kind of a way that we're currently thinking of doing multiple vehicle simulation and then still maintain the ability for them to communicate back and forth with each other. Let's go to the next slide. And then this is getting into more of that hardware realm. So a lot of what I've been talking about is more in the software and simulation realm. And so if we have all of these simulated components, if we have things like orbit propagation, attitude modeling, modeling of the environment, then we obviously want to be able to communicate out to hardware. And also in the same way that we're abstracting interfaces to these federates, we also want to abstract the interfaces out to hardware. So, you know, the ideal scenario is I plug a single board computer into a piece of ground support equipment, pick a couple of ports, and data starts flowing out. That's a great nirvana one day. But so we're trying to get close to that. You know, we're working on how we actually bridge out to kind of industry standard EGSE, like a National Instruments PXI system, basically just providing out all of the different kinds of interfaces that we might need to test various pieces of hardware. And this also goes to some of that autonomy testing if we want to run various autonomy software on representative hardware. So if we go to the next slide, and then this is just sort of a continuation of that, you know, nice pictures of our hardware that we have going with our NI Pixie, and basically just, you know, utilizing a variety of C APIs and things to ensure that we're kind of abstracting away that connection between a piece of hardware and our central broker. We're using things like XTCE as well to help. That's an industry standard for basically describing telemetry packets. And so in that way, we can kind of have this almost data pipeline going from our Amigos common object model all the way out to a formatted CCSDS packet that a flight computer can use and read properly. So we're kind of working through all of those steps, making sure that all of those kinds of minutia details are abstracted away from users so that we can be a lot faster and more responsive when we want to set up these simulations. So go to the next slide. And then this is sort of just our long-term vision for this project. So basically, you know, we're wanting to set up these initial simulations, test out our, you know, initial models, and we've kind of been calling it like zero or first order federation, basically creating a lot of low fidelity models to build out this overall capability. There was a great comment earlier about using CubeSats as sort of the test bed for a digital twin because they are fairly simple. They have one component, you know, for each subsystem. It's a nice and easy way of developing these digital twins. And so we're using our own internal AeroCube projects as sort of those reference missions and building out capability from that, but then making sure that as we're building out those models, they're not siloed into just those AeroCube missions. So, yep, I think that that's my last slide. Are there any questions? Or Denver, do you have any wrap-up statements?
Well, yeah, I'll just wrap up real quick and highlight that. Yeah, so we've had an opportunity to hear from the great work that Rob and Dexter are doing, and what we're doing is taking that and tying that back into our larger framework, right? So Rob's work fits inside of that service category. It's a functional capability of the twin. It's what the user's interacting with, and then what Dexter showed here is one of the many aspects of our connection dimensionality, right? So it's the thing that sits in the middle that pulls everything together and helps make this actual system functional. And so between the two of these are just some of the glimpses into what exists in those domains and how we are taking those and leveraging those into a larger digital twin as a virtual system. And so, yeah, and we would love to answer any questions that people have on this.
Great, thank you guys. I don't see anything in the comments. Okay, does your MBSE model capture these additional connections? Is a question by Timothy.
So yes, we are working our MBSE model to connect across all of these. And so if we may have a quick view of it up here. Let me see if we could get there. So you can see where our MBSE model, we generally use Cameo here. A lot of times we're trying to identify, okay, where does the ASOT reside? Does the ASOT reside within the MBSE model? Does it reside somewhere else? And how are we pushing that data back and forth? So we're identifying, Aspen's a great example of that right now. So we're using Aspen to federate our power models, and we're identifying where do the parameters associated with those power models reside. And there's a lot of them reside in Cameo. So parameters around the battery or the solar panels or the reaction wheels and things like that, those exist here in the Cameo model, and they become inputs into the Aspen simulation that is integrating all those power models together. So yeah, we are building out connections across our MBSE model to the broader virtual system. Looks like there was another question. Yeah, how do you resolve ASOT struggles? That's an excellent one, and is one of the big challenges that we've seen here. And it's not even just ASOTs. Sometimes it's just coming to commonality on what we call parts and components. So for the ACOM model that Dexter referenced, the Amigos Common Object model, when you're bringing in different domains, they may describe, we had this issue with the power models. They describe components and units and parameters differently. So bringing everyone together to come up with a common description is critical. And so as part of that conversation is also where you start to have that conversation on ASOTs, right? So where are we going to identify or store the ASOT? How do we know that it's trusted? How do we know that we're pulling from a accurate repository? So it's in that, we've noticed that it's in that early stages of the project. You're having to come to agreement on what do terms mean, how are we leveraging them and referencing them. That is also a great time to go through and have those same conversations about, okay, where are we going to maintain the ASOT for this piece of data?
Okay, with that, we are at the top of the hour. So I'm just going to do some quick closing statements and slides, and then if you would like to, we can keep this channel open for a little while longer if anyone wants to continue any conversations. But let us just have this last little bit out of the way. So thank you to all of our presenters today. We will be providing, well, following this event, you can expect three things. First, a PDF of the presentations will be available for download on the SEF archive site following this. Second, the recordings of these events will be made available on the same archive site, linked through linking to the YouTube channel once our security team completes the review. And third, a quick 3-minute survey will be provided to attendees to garner feedback. Any feedback is absolutely appreciated, so please let us know how we did. If you have not done so already, please join our mailing list to keep up to date on upcoming events. And with that, thank you for attending. That concludes today's System Engineering Forum. We wish everyone a wonderful day. And so I will stop the recording now. And then if anyone wants to continue the conversation, you can.